is you're going to get a struct point on the left-hand side of a dot. So I can say some struct point dot flip, right? Oh, and by the way, that thing you get better be a mutable reference or a mutable thing. The compiler will turn it into a mutable reference and pass it as the first argument. So this is how we get the dot syntax. We're just like, no, the first argument happens, if you call it self inside an impl, will be the thing to the left of the dot. Fair enough? And so now the flip function can do whatever it wants to do. It can, in this case, swap the x and y values, which it can do here because partial moves are a thing, and because you have mutable access to the struct. And so now we're all cleaned up and have flipped the two coordinates. This is a way to make a thing that points like this, point like this, and so let's take a look at how that's called down here. There's p.flip. Is p a mutable point? Indeed it is. The compiler takes the mutable address of that mutable point and passes it as the first argument for the flip primitive. So we have some other methods here. Flipped takes an argument by reference, not mutable reference, because it's not going to change anything in it. And again, whatever's on the left of the dot has to be something that's convertible to a reference to a point. It passes that in as self, and then it gives you, in this case, a new point representing the flip value. So I could have called .clone.flip. I could have implemented this as clone and then flip, right? But I instead chose to implement it separately as just return a flipped copy. Make sense?
For the reference to self argument, that means that we could pass just a point or a mutable reference to a point or a
Yeah,
reference to a
as
point.
long as the compiler sees the thing on the left-hand side of dot is safe to convert into a reference to a point, it will do that. That is correct. And in particular, that reference, that's a borrow, so all the borrow rules apply, right? While I've got it borrowed, nobody else can borrow, nobody else can borrow it mutably, nobody else can, even the owner can't change it. All those borrow rules apply while we're inside the flipped method. So you gotta watch out for that. You kinda gotta know how these dot blah methods take their argument, because you have to know which borrow rules apply, right? The third case, the borrow rules apply as well, except in this case it's just the ownership rules. The collapse thing actually consumes the thing on the left. So it better be an actual object. And so afterwards, since it doesn't return it or anything, that thing that is passed in by dot is dropped now. Which is okay, because we're going to collapse the point down into the sum of its coordinates. Yeah? So let's look again at the caller of all this. Look at our main program.
Is there a reason that there's a space in flipped where you're calling self.y and self.x?
No, it's called bad. Thank you. That should look like that. Thank you. There's nothing magic there, it's just bad fun. Don't do that. Mute p is a new point. With value 3, 4, okay, I can do that, right? We know how that works. And then we're going to print its flipped coordinates. We're going to flip it and print its coordinates. How come I can print it? Oh, because I'm using the debug thing, so that would be good. And then we're going to collapse it and print the number we get back from the collapse. Clear enough? So I think in this case we should see printed 0.43, 0.43, and 7. I think that's what we should get printed. Let's see if it all compiles and runs. Okay, look at that. Just like we did. So that's that, yeah.
For the collapse function,
Mm-hmm.
this is a decision that you make as the person who's defining these functions that collapse is going to consume.
Yep.
Because you could have put a reference
I can absolutely put a reference there, right? Another real common pattern would be, that wouldn't make sense for collapse, but might make sense for something else, is to have it take ownership of the parameter and then return that same parameter. Because it doesn't drop it automatically, it only drops it when it can prove it's not reachable anymore, right? So yeah, you gotta decide. This is part of API design in Rust is, what do I choose for each of these inputs? Just a second. A really common place where you might do this is in a situation where you really do want to guarantee that nobody will touch the darn thing again, right? Let's say I have some security token, right? And I'm now about to spend the security token with some network transaction. Really, I should take ownership of that security token and drop it when I'm done. And that way you can't have program bugs where later I try to spend the same security token a second time. That seems like a good idea. So you get all these type level guarantees that way, which is kind of. That said, the vast majority of impl methods probably use ampersand self or ampersand root self. It's sort of the default.
Earlier you used impl and in the struct point. Does
Yeah.
that tell the compiler that all these functions belong to this struct point?
Absolutely. So I can only call, I have to call p.new where p is some point. I can't just call new by I can call new by itself, but I have to pass that extra argument, which is a point. I can't call, q.new where q is a number, because there's no impl of new for numbers, it turns out. Right? Or sorry, new's a bad example. q.flipped where q is a number, because there's no impl of flipped for numbers. Right? So yeah, this is the type checker is sorting all this out. The type checker is statically deciding which methods, which associated functions.
So then that point almost functions more like a class, I guess, than a struct?
Yeah, this is sort of C++'s vague, weird idea of object-oriented programming, is the idea that sort of the compiler, rather than the runtime, normally decides which method to call. That's sort of what's happening here. It's like, it's not a class, right, in the sense that there's no vtable here, right? There's none of that stuff. The compiler optimizes, figures out what it wants to do and turns this all into function calls. If you squint at it just right, it looks kind of object-y. This is sort of a concession to the object-y people as much as it's anything else. It's very, very common to use. So this is probably the key idea of today, if I had to pick the key idea of this today. Let's keep going a little and look at other implications. Notice that this allows you to chain the operators together, right? I can write p.flip returns a point, right? No, flip doesn't return anything, so I can't change this. P.flipped, right? I can write p.flipped, which returns a point, dot flipped, right? Now that point's going to get passed in as a reference and returns a new point, dot flipped, and everybody is perfectly happy with that. I'm wasting a lot of memory and ending up, let's see, and so that's a thing I can write, and the compiler's perfectly happy with it. And that's part of why this syntax is in Rust, is because it makes it convenient to say, well, take the output of that function and turn it, use it as the input to the next function and so forth in a way that's maybe a little easier to read than if you do that explicitly. Make sense? Otherwise, you end up doing some nesting. Nesting's hard to read.
There's like no difference between p.flip and flip with p as its only argument.
Right, except I'm not even sure you can call it that way. I can't even remember anymore because no one ever does. Let's see, point, colon, flip, and you p. Let's try that and see what happens. I'm going to say it won't work, but I'm not positive. That works, huh, who knew? Yeah, so no, those are exactly the same thing. You would never write this in practice, almost never write this in practice, but it is apparently a legal thing. Yeah, and that's all that's happening. It's this thing, oh, that thing on the left, I can take immutable reference to that, and I'll pass it as the first argument to the flip. Yeah? play with this, get comfortable with it. You're gonna be using it a lot and lot and lot in Rust. It's a thing that's done every year. You notice we keep saying derive, 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 derive. What the heck is with derive? You know, there's this funny attribute syntax floating around, one of Rust's 50 different syntaxes. The attribute syntax is used for compiler directives, tells the compiler to do something special. In this case, the special thing the derive directive tells it to do is to say, well, if all the fields of this struct are debug, then figure out how to make the struct itself be debugged. If all the fields of the struct are cloned, then make sure that the struct itself is cloned. And the same for copy, partially, partial order, right? So now I can use a temperature just like it was any other kind of number in a lot of ways. Not all the ways, because we haven't derived enough things yet or implemented enough things yet. But I can do sort of a thing here. Let's take a look at an example. Oh, here's a discussion of pattern matching we should have read several days ago. Fantastic. Anyway, notice we're using pattern matching here to dig the actual inches out of this inches struct. It's up here, and so now I've got this conversion that does 2.54. We'll make a new centimeter struct. And so the point is that, you know, we're using these things. There again, this is all an example about new typing. We're making new types so that we don't screw up. Remember when we lost a Mars rover a while back because they screwed up between metric and imperial units? We're trying to make sure that, borrow the Rust type system to make sure that that doesn't happen again. If the line had been written in Rust and written properly, we might not have lost the line. Yeah. And pattern matching applies to structs, just like anything else. You already saw an example of it a second ago. But it's especially important for tuple structs, because otherwise you use .0 and .1 to take them apart. There's tuple pattern matching, there's slice pattern matching. These work exactly like you think they do, right? X is bound to the value 3 in that first line, and H is bound to the value of hello. And of course, the fact that those are explicit constants on the right-hand side doesn't matter. If I'd had some variable bound to that tuple, the same thing would have happened. And so pattern matching can be used to do what's called deconstruction. I'm going to deconstruct my thing into its component parts. And like I say, in struct world, that's a pretty common thing.
Is a tuple struct the same thing, or is like a tuple the same thing as a nameless tuple struct?
Yeah, yeah, absolutely. They really are pretty much the same. You know, you have to declare tuple structs, and so you know what types need to go in the fields. When I use an anonymous tuple, the compiler infers what types you're using in the field typically. And so there's all different tuples of size 2, right? There's the tuple of size 2 where the first one's an int and the second one's a string, and the other way around. There's a lot of different ones. And, but, you know, the compiler takes care of making sure that you don't, for example, compare two tuples that are of different types. Or take the 0th element in an if statement when the two tuples are of different types. That there's this notion floating around. I don't know why this slides are here. They really should be way earlier in the course, but we're here now. We'll deal with them. Refutable patterns and irrefutable patterns. On a let, the compiler has to be able to prove that the deconstruction will always work. If you pass something and it can't prove that you could actually take it apart the way you're saying you're going to take it apart, then the compiler refuses to compile it. That's what's called an irrefutable pattern. For a match statement, the compiler, you know, for each of the match arms, right, there's a pattern. Well, obviously that pattern has to be able to not match. That's a refutable pattern, right? Some pattern has to match, but no particular pattern has to match. And that's an important distinction, and you got to watch out for it.
Interesting, so this is a very, very fancy struct pattern matching example. Do I care to do this today? I don't think so. Here we're matching a point against some patterns. And those patterns are pretty fancy. It turns out that x colon x at 1 dot 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 3 means the pattern matches anytime the point has an x struct whose value is between, x field whose value is between 1 and 3, exclusive, and the dot dot in that pattern means, and I don't care about y or anything else, I just care about the x field. The x at part means give that matched value a name, in this case x, that I can use in the match. The next one is a more straightforward match, and otherwise I get a panic bad point, because remember, the match has to be able to match every possible point value. We haven't come close to that yet. So when I run this, it should work. It does. It produces 3. It produces 3 because here, I think. Anyway. Yeah, patterns are weird.
What's the difference between the triple dot and the double dot?
The triple dot denotes a range. The double dot just denotes, the triple dot is for guards, for the pattern itself, and the double dot is for, structs. It's sort of ignore the rest of the struct. So the first one is check this particular field, and the second one is ignore the rest of the struct. So there's a little each floating around in there. You don't necessarily, at this stage of your Rust career, have to be comfortable at that level with the pattern matching syntax. It isn't very often that that kind of thing actually comes up. Having said that, reading the sections on pattern matching in the book and in the Rust documentation is a cool thing to do. It'll make you more of a Rust guru, you know that. All right. Continuing onward. Pattern variable modifiers. Oh, right, in pattern matching, you can use mute, just like you could in anything else, so that the pattern, the thing stored in the pattern variable can be changed on the right-hand side of the match arm. You can also use ref to say, no, I don't really want the thing itself, I want the pattern to refer to the address, the reference to the thing. And so it's a way to get an address into a pattern sort of in a fun way. There again, you don't use it that much, but it does come up. The book has some really, really nice, albeit not super important, descriptions of how Rust lays out a struct in memory. I mean, the sort of short answer version of how does Rust lay out a struct in memory is it's not well defined. Compile can do it however it wants, and it may change over time without warning, so you can't count on any particular struct layout. If you want to count on a particular struct layout, you can say repr packed or repr C as compiler attributes, meaning respectively lay it out like it was a C struct and lay it out like, with all the fields jammed together in order as close as you can get them. If you're doing device drivers or something like that, for the rest of you, you probably just start mostly. In particular, the Rust compiler, unlike the C compiler, is very, very happy to reorder all your fields so that they're very tighter, so that you can have a key space in your structs, which can be a nice efficiency. Because there's no arithmetic on, pointer arithmetic on struct fields, the compiler has a lot more freedom to lay out the struct. So that's the 45-minute tour of Rust structs. Definitely read this chapter in the book. Definitely practice some of these struct things. In particular, get really used to impling structs, because impling structs is a fundamental, normal Rust behavior. Other questions or concerns? All right. Looks like we have time to read ones too.
Oh, we have.
Yeah.
Is it common, so in libraries like XCB or something like that,
Yep.
where you get back a gigantic struct from something, is that something that's common in Rust too? I've seen it in some examples, but.
It can happen, it can happen. Rust, you know, Rust more so than C in some ways, because in C, one of the ways you avoid that sometimes is by just sticking the struct in some static storage and returning a pointer to it, and hoping that the pointer is still good at the point where the person dereferences it, right? Rust doesn't really have that whole hope that the pointer's good at the point where the person dereferences it thing going on, and so returning those things by address is hard, and so people typically just make a copy, you know, whatever, make an allocated new thing and return that. Yeah, it's definitely a design pattern. The other thing that Rust does, that C does sometimes too, is instead of returning it, you pass a mutable reference to such a thing and then whack on its fields. You know.
Is that considered like reformed C programmer behavior, or?
Yeah, it's a little bit reformed C programmer behavior. It's not even very good C programmer behavior, and you have to think really carefully before you do that. There's sometimes efficiency reasons why you choose to do that, but there again, don't ever make your code more efficient until you've measured, and the same goes for not returning a big struct from a function. It's like, well, maybe it matters performance-wise, maybe it doesn't. You know, probably not, and if it does, then you're gonna find that out when you find your program's running too slow, which you might never do, and you measure the performance, which, you know, you will do as the first thing when you find your program's running too slow. Or using too much memory or whatever pathology you've got. One of the nice things about Rust, as opposed to the garbage collected languages, is if I return a giant struct in Rust, it's guaranteed to be dropped reasonably soon. It doesn't just blob up the heap until the next GC whenever that happens to be. And so the level of cache pollution is a lot less in a Rust program.